Okay. Great. Good morning, everyone. Welcome to this week's distinguished webinar series in AI and cybersecurity. Today's talk is by Dr. Bodhisatwa Mazumdar. Correct me if I pronounce it.
Yeah, perfect.
He's Associate Professor at the Department of Computer Science and Engineering from IIT Indore. And his talk is titled today is Variants of Fault Analysis Attacks on NIST Lightweight Ciphers, an Emerging Security Threat. Dr. Mazumdar is an Associate Professor in the Department of Computer Science and Associate Dean of R&D at IIT Indore. He received the Master's and Ph.D. degrees from IIT Kharagpur, India. He was a Postdoctoral Researcher in the Design for Excellence Laboratory, New York University, Abu Dhabi, UAE. His current research interests include optimized hardware implementation of cryptographic primitives and side channel attacks and countermeasures. He is presently a working group member in IEEE Standard 1413 on Guide for Selecting and Using Reliability Predictions, and IEEE 1624, which is the IEEE Standard for Organizational Capability. Dr. Mazumdar has been a technical program committee member for various conferences such as VLSID, SPACE, and VDAT. Dr. Mazumdar, it is an extreme honor to have you as part of the webinar series. And, we are so grateful for you agreeing to our webinar, and I appreciate the time and effort that you're going to put forth for this conversation. I'm sure there are a lot of interesting discussions that we're going to have today, and I look forward to collaborate with you as we go along.
Of course.
Thank you so much.
Thanks, Professor Prakash, for the wonderful introduction. I will just share. I hope the slide is visible.
It's coming. Let's see. Yeah, I think we can see it. Great. You can proceed. Yes.
Okay. So, hello, everybody. Good morning in US and good evening in India and to the rest of the world. So, the title of this talk is Variants of Fault Analysis Attacks on NIST Lightweight Ciphers. So over here we have certain keywords. The first one is the fault analysis attacks, and the second one is the NIST lightweight ciphers. So what is a fault analysis attack? So suppose when we have a class of, say, encryption or decryption algorithms that is deployed in a hardware, and if that hardware is deployed in a field, okay, and during the execution of that hardware, okay, due to certain environmental mechanisms, faults can be injected in such encryption and decryption algorithms when they are in execution on such hardware platforms. And as a result of those fault injections, those encryption decryption algorithms, they may leak information about the secret key that is embedded within the device. Okay, so fault analysis attacks, they have been in the literature. It was first explored in the year 1999, and over the last 2-3 decades, okay, there have been optimized attacks mounted on such encryption and decryption algorithms. And recently, NIST USA, they came up with a standardization perspective for the lightweight ciphers. So the lightweight ciphers, they are targeted for implementation on IoT devices, okay, and such IoT devices, okay, they usually process data of the user who is using that device, and as a result, certain data privacy aspects they come into the picture, okay. And when faults are injected in such lightweight ciphers, okay, they may play a havoc, okay. So in this lecture, we will see what are the different types of fault analysis attacks that exist, that have been mounted, and we'll see certain countermeasures as well. So to begin with, a brief overview of my research domain. So my research basically pertains to the domain of hardware security. Okay, so when we come across the term security, we come across terms such as identification, that means the identification of the user or validation of the user. Say suppose there is a sender and a receiver. If there is a one-to-one communication, it must be private, okay, to ensure the data privacy. There could be certain applications such as electronic signatures, access control mechanisms, electronic purse, and digital right management. So in almost all of these applications, okay, means you need to embed certain security features in such applications. Okay, and basically when we consider the security applications, the cryptography, okay, certain cryptographic primitives, okay, they form the benchmark or they form the foundations in such applications. Okay, so there is another aspect of security that when we are concerned about hardware. So first term is the hardware security, which deals with the secret data. How can we protect the secret data when we run algorithms on the hardware? So that domain is related to the hardware security. The other domain is the hardware trust, in which we try to design and manufacture hardware devices so that it addresses the trustability issues among the different manufacturing components. So say consider the VLSID design industry. The design house can be in one geographical part, say in US or in India, whereas the manufacturer or the fab house can be in other geographical parts, say in Taiwan or in Vietnam. So as this design industry is spread over multiple geographical regions, many a times it happens that the trustworthiness becomes a question. So in such an environment, how can we build trustworthy devices? So that perspective comes in the domain of hardware trust. Okay. Whereas when we talk about the hardware security, we talk about how do we impart security features to the data with respect to the data. Okay, and that data can be stored in the memory. When the data is stored in the memory, how can we impart security features to that form of data? And when the data is in transit, okay, how can we impart certain security features? So when we talk about security features, they can belong to different classes. So the first class is that of confidentiality, in which in confidentiality we ensure that the message that is being shared between a sender and the receiver, that message should be intelligible only to the sender and the receiver and to no other eavesdropper. So an eavesdropper may be snooping on the communication link between the sender and the receiver. To such an eavesdropper, it must be completely unintelligible. The next aspect, the next class is that of data integrity. So data integrity features, it ensures that when a data is in transit or if a data is in storage, and if such a data, if it is tampered, okay, then it must be detected. Okay, so such features are called data integrity. Then we have the authentication. In authentication, okay, the sender, when he or she is sending the data to a receiver, okay, he or she must authenticate himself or herself. The sender must authenticate itself. Okay, otherwise the receiver will not be sure from which source the data is coming. So authentication is also an important application. Then you have the non-repudiation. The non-repudiation is the act of denying. Suppose when a sender has performed a financial transaction, at a later point of time, he or she may deny of having made such a financial transaction. That act is called the repudiation, and to thwart any such malicious acts, okay, such features are called the non-repudiation. So typically we use digital signatures to implement such features of non-repudiation. And the last part is that of the availability. So in availability category, the data must be accessible to the authorized user 24/7 cross 365. That means the data must be available to the authorized user at all points of time. So that guarantee must be given. So these are the different categories or applications, okay, wherein all types of security features they belong to. And for such security features, the cryptographic algorithms, the cryptographic primitives, okay, they play a very important role. So whenever we see a wide range of cryptographic primitives, they have been proven to be mathematically resilient. But when it comes to the implementation perspective, when you come to the implementation aspect, even being mathematically resilient, mathematically robust, the implementation itself leaks certain information about the secret key that is there in the device. Okay, so challenges remain that how can we minimize or mitigate such leakage, that information leakage. Okay, so the class of attacks that mount such types of attacks are called the side channel analysis attacks. Okay, and the spot analysis attack that we will discuss, okay, that belongs to the class of the side channel analysis attacks. So over the last 2 decades, hardware security has become increasingly important. And we have seen there are numerous attacks that have been mounted. Okay, so in June 2022, MIT researchers discovered a major flaw in the Apple M1 microprocessor. Then researchers at ET Zurich, they mounted an attack called the SmashX CPU attack technique. Okay, so this was proposed in October 2021. Then there was another Taiwan Semiconductor Manufacturing Corporation. Similarly, there have been a wide variety of attacks. So if you see the literature of the past 2 or 3 years, there have been a large amount of attacks that have been mounted. Okay, very important. So what does hardware security basically do? We basically implement encryption algorithms to secure data. Okay, and how do we implement the encryption algorithms to make them secure? Means such implementation should not leak information. Okay, so we are bothered about storing the encrypted data with strong access control mechanisms. Okay, authorization mechanisms should be extremely tight, and we should prevent unencrypted data from existing in an idle state. If there is an unencrypted data, that data should not be accessible to the external world. And in US, okay, the NIST USA, they have laid a fifth standard, okay, that lays down the instructions or the rules for such hardware security implementations. Okay, the bottom line is that we need to have optimized encryption algorithms. Why optimized? Because we are talking of lightweight ciphers, and in lightweight ciphers, okay, they are implemented always on the resource-constrained platforms. So we are thinking of optimized encryption algorithms that needs to be secure, thoroughly secure. So one such application of hardware security is this trusted platform module. So the trusted platform module, it ensures, okay, most of the security is we discussed regarding the confidentiality and so forth. So this trusted platform module, it contains a cryptographic processor wherein we have the true random number generators or the pseudo random number generators. We can have the public cryptographic primitives, okay, so, different kinds of encryption and decryption or digital signature engines, depending upon the applications that it caters to. And we can have different memory segments as well, okay, persistent memory, okay, which is used to store the keys. Okay, so there can be different variants of key, and there could be versatile memories. Okay, so each of these memory components, they may store different types of informations. So coming to the implementation aspects, okay, so we are bothered about how do we implement such cryptographic algorithms, okay, that can be deployed on smart cards or crypto cores or crypto processors. Okay, how do we design such hardware security modules, okay, that would be resilient to these kinds of attacks. So this is a typical processor architecture with secure data processing. Okay, so in this case, what we see is that this is a typical von Neumann architecture in which you have a control unit, you have an ALU, the data address register, the program address register. So you have an instruction path, the data path. Okay, and according to the requirement, you may have an ENC block. The ENC block is basically the encryption block. Then you can have an isolator. Okay, so the isolator basically segregates which part of data must go to the secured branch, which part of data, data flow will go to the insecure IO controllers. Okay, so you can have an isolator, you could have a decryption engine. So this is kind of an architecture that is based on the von Neumann architecture. Okay, so there are different types of challenges that exist in hardware security. Okay, so this picture, it tells you about a person may have an implantable device such as which monitors the heart rate monitor. Okay, incorporating security. Okay, as secure, whenever you implement a security feature, it draws power. Okay, it draws a battery power. So whenever we use implementable devices, they are mostly battery operated. Okay, so any security feature that you will implement, it will lead to additional withdrawal of power, and that would reduce the lifetime of the device. Okay, so how do we implement encryption algorithms in such devices? Okay, and if a fault is injected in such devices, it may lead to loss of life. lives of the patient as well. Okay, so I was saying of different types of side channel attacks. So what is the side channel attacks? So the side channel attacks, what happens is that, let's suppose we have a hardware ICs, okay, and when they are running on a certain platform, say it can be an SoC or it can be a PCB, okay. So on such platforms, they may leak information through the power side channels, through the electromagnetic side channels, through the optical side channels, and so on and so forth. So from each of these channels, an attacker can gain significant information about the data. For instance, suppose you have a register that is there in the device, and whenever the data is changing across a device, okay, it creates its signature in the power. So if an attacker, if he can precisely capture the power corresponding to a particular register, okay, then he can get significant information about the intermediate data. And if that intermediate data, if it is a function of the secret key embedded within the hardware, then different types of attack tools, through different types of attack tools, one can mount an attack. So one such important attack tool is the mutual information analysis. And presently there have been a plethora of ML algorithms, okay, that have been proposed to mount such attacks. Okay, so the side channel attacks, they are often passive attacks. Then the next class of attack is that of an active attacks, that is the fault attacks, in which faults are injected in such ICs, and as a result of faults, okay, you get faulty ciphertext or faulty encryption operations. Okay, and as a result, you can build a system of equations involving the fault-free operations and faulty operations. So you can have two categories, faulty operations and fault-free operations. And as a result of that, okay, you can solve that system of equations to get information about the secret key. And for such attacks, you have test infrastructures as well. Okay, so when we talk about fault attacks, what we are discussing is that, let's say suppose you have an IC, and say suppose inputs or messages, okay, are being given as input to such ICs, and when an encryption algorithm is running on such an IC, and a fault is injected during the execution, it may lead to an error. So these errors are called the faulty outputs or the faulty ciphertext, okay? Whereas if a fault is not injected, then they are called the fault-free ciphertext. So you can devise a system of equations involving the fault-free ciphertext, the faulty ciphertext, and the embedded key. Okay, so it is a very transient faults can be easily injected in such electronic devices, and hence this type of attacks, they form the strongest variants of attacks. So when we talk about the history of faults in the system, right from the year 1950s, okay, anomalies existed in the electronic monitoring equipment, due to which there was a controllability issue in the ground nuclear testing. Similarly, in the aerospace industry, okay, such ICs are critical ICs. Okay, so the problems in the space electronics, they lead to the soft phase. And from 1980s onwards, okay, we have been observing that due to the radiations, okay, UV radiations, okay, the semiconductor electronics, okay, the functioning of the semiconductor electronics, they can go haywire. So this is a typical demonstration of a fault analysis attacks on the AES block cipher. I have not discussed the construction of AES block cipher. It is the most standard block cipher. So in this case, okay, when we have an AES block cipher, it comprises of 10 rounds, round 1 to round 10, and each round contains different operations. That is the key mixing, the substitution layer, okay, and then the permutation layer. The permutation layer comprises of 2 layers, the shift rows and the mix columns, okay, and then it invokes the next round. So each of these rounds performs the same set of operations other than the round 10. Okay, in the round 10, you don't have the mixed column operation. So basically, this is the fault-free branch in which you don't inject a fault, whereas this branch is basically the faulty branch in which you inject a fault in the round 9. And as a result of the fault injection, okay, from round 9 onwards, you have the faulty data that is being transferred, on which the operations are being done. So in the right branch, you have a faulty ciphertext, it is C star, whereas in the left branch, you have a fault-free ciphertext. Okay, and you have these unknown variables, that is the keys. So what you can do is that as all of these are bijective functions, you can easily backtrack, okay, in this branch as well as in this branch, and you develop a system of equations. Okay, if the system of equations are insufficient, you perform more queries. You pass on more increasing number of messages, so that it gives you an enough system of equations, so that you get significant information about this secret key. Okay, so this example, what I said is about the differential fault analysis, in which you create the differentials at each stage. So in this case, okay, you create a differential between C and C star. So differential means the bitwise OR operation. So at each stage, you make a bitwise OR operations, and you see, okay, how the ones, that is how the fault propagates across the different operations. So if you create a trail, of the fault, okay, that gives you pointers, okay, that which are the different hotspots in that algorithm, okay, which you can attack easily. Okay, so you can execute the cryptographic computation twice with a plain text and no fault, that is called the fault free, and with the same plain text and the fault injected in the penultimate round, that is called the faulty round. And you can import the key information from the output differential. So depending upon the encryption algorithm, okay, you fix your round that, okay, I would inject the fault in this round, okay, so that it leaks maximum information. Okay, so that category of research that belongs to the that pertains to exploration of the faulty hotspots, or the exploitation fault exploitation space, exploration of the fault space. So this is a typical block diagram for the differential fault analysis attack. So the upper branch, okay, so that is the key scheduling branch, and the lower branch is the actual data path. And in the data path, you inject a fault in the round 9, and as a result of the fault injection, the fault propagates. If there was no fault, you would have got C. In the event of a fault injection, you got the faulty ciphertext C star, and then you can create a system of equations by tracking backwards, okay, and involving the keys. So this is a demonstration of a fault attack on the RSA encryption scheme. So RSA is a famous encryption scheme called the Reverse-Schmidt-Edelman. Okay, so in this case, okay, so in the decryption operation, it is basically an exponential operation. So over here, Y is your ciphertext, that is the encrypted data, and it is encrypted, and it is exponentiated with the private key to get the plain text, resulting plain text. So when a fault is injected in the key register, that is when A transforms into A hat, okay, you get a faulty, you get a fault-free plain text and a faulty plain text. So here it should be X hat. So attacker has access to both X and X hat, and as a result, the attacker can compute the ratio of both the fault-free and the faulty plain text and get an information about the A minus A hat. So we have a small example case study over here. So suppose the fault is injected in the ith bit of A, say I equal to 2. And so suppose A is basically a 6, 0110. We are taking a 4-bit keyword. And as a result of the fault injection in this bit, 0110 transform to 0010. And as a result, we can compute the A minus A hat. A minus A hat is 2 raised to the power of 5. So an attacker knows Y, the attacker knows X and X hat. And when he computes the ratio, he can get information about A minus A hat. So this is the case when the fault transforms the bit 1 to bit 0. What if the other way around? If the fault transforms the bit 0 to bit 1, then the attacker obtains minus 2 raised to the power of 5. So if the attacker has information that which bit was transformed, then he can get significant information that how the key register has changed. And this is a significant information, okay, of the secret key that the attacker can compute. So just by injecting a fault in the key register, he or she can compute, okay, what was the difference between the fault-free key and the faulty key. So this is a very strong attack, okay, and it has led to devastating effects in the field. But over the last decade, okay, different countermeasures have been proposed. So we'll discuss about the countermeasures as well. So basically, what we see is that when we talk about the fault attack space, okay, so basically this data, whenever the data goes from one device or from a sender to a receiver, okay, it follows a specific communication protocol. That protocol can be a Zigbee protocol, that protocol can be a Bluetooth, okay, and so on and so forth. And And who abides by such protocols? The cryptographic primitives which impart the security. And these cryptographic primitives, okay, they have certain arithmetic operations. They execute certain arithmetic operations. Now, how these arithmetic operations are executed? They are executed on the hardware platform. So now, when we talk about the fault, okay, the fault is injected always in the hardware. That means either in the ALU, in the registers, or in the memories itself. Okay, and all of them, they form the part of the RTL. Okay, that is a register transfer level. And this register transfer level, when we go one level beyond, this RTL, when you synthesize an RTL, they are synthesized in the circuits in the form of gates and flip-flops. And gates and flip-flops, they are basically built from a set of transistors. So basically, when you inject a fault, you are basically bothered about this RTL implementation. So how do you implement an RTL that will be resilient against such fault attacks? So there are different types of fault models. A fault can be injected within a byte. Okay, so you have an 8-bit. So within a byte, faults can be injected into multiple bits. It can be multiple. It can be injected in a single bit. It can be injected in multiple bits. Okay, the fault can be injected over a word, that is spread over a word, or the fault can be injected over an entire word. Okay, so larger the number of bits counts that the fault toggles, okay, the more harder will be the attack mounting. If you are able to inject a fault in a single bit register, then in that case, mounting the fault attack would be much easier. But injecting a fault in a single bit register, it is very hard. Okay, that means you need to have such a precision setup in that case. So when coming to the fault attack, we are bothered about the granularity. That means what power does the attacker have? That means what is the attacker's threat model? Can the attack infect a single bit? Can the attacker inject a fault in some bits? Or can the attacker inject a fault in an entire word? That is how many bits are affected by the fault, and that lays the foundation stone of how the attack will progress. Then the fault type or the modification, that is whether the attack is a stuck at fault. That means if an attack is injected within a particular register, okay, that value will stay, okay, until and unless you turn off and again turn on. Okay, so such type of faults are called the stuck at faults, which remain, okay, even after multiple operations. Okay, even after multiple power off and powering on the device, such faults remain. So they are called the stuck at faults. There can be a flipping fault. So these are the transient fault. That means you inject a fault for a certain amount of time, and after certain operations happen, you can withdraw the fault. So they are the that wherein you have an absolute controllability. The other class of faults is a random fault, in which you randomly flip certain bits within a register. Then you have the control aspect. Okay, you can precisely control a fault, you can loosely control a fault, or you have no control on the fault injection. And the next class is the duration. That means for how long you are keeping the fault. Okay, for how long that fault is effective, whether it's transient, permanent, or destructive. So these are the different categories in which you can classify your fault models. So we have different types of fault injections. Okay, some can be non-invasive, some are semi-invasive, and whereas some are invasive. So there are numerous fault injection setups that exist. Okay, and a typical fault injection mechanism is injecting glitches in the clock train. Okay, so when you inject a glitch within a clock cycle, okay, that induces metastable conditions within the registers, as a result of which certain instructions may not be executed. Okay, and when certain instructions are not executed, that means instructions are skipped. Okay, this may lead to faulty computation. So this is a setup that shows, okay, that type of a fault injection setup. So faults can be injected through a set of clock glitches. Faults can be injected through a set of voltage spikes. That means underpowering the device. So suppose your voltage, the power suppose your device is running at 1.5 volt. Okay, and for say suppose a 1 nanosecond or say 2 nanosecond, you just underpower the device, and as a result of that, okay, certain register that may get corrupted. Okay, so that models a fault. Okay, so as a result of the fault injection, okay, it has devastating effects on the program flow. Okay, certain instructions could be skipped. Okay, certain instructions, okay, that can be modified. Okay, loops means control can go out of the loops, or control or when you are executing a conditional statement, okay, that may take the pause branch. Okay, so suppose if you have an if branch and if you have an else branch, instead of going to the if branch, okay, the control may go to the else branch, and that would lead to the faulty execution. And you can have effects on the data flow. That means you can inject fault within a register that would lead to computation errors, or you may corrupt memory pointers if you are injecting a fault in a memory. So these are the different variants of fault injection setups, okay, that have been there in that exist in the literature. There are other variants such as underpowering, temperature. Okay, you vary the temperature abruptly. Okay, that leads to a fault injection. And then you can have optical fault injection setups as well. You can have EM fault injection setup. Okay, that means you inject a fault using the electromagnetic variations, and that induces eddy currents within the device. Okay, and that absolutely changes the certain data values within specific registers. So this is a typical example of a fault analysis on the AES block cipher, in which, okay, you see that once you inject a fault in the beginning of round 9, you propagate, you execute the substitution layer. Okay, the fault changes from F to F dash. Okay, certain bits within the register, they get faulty, and after the shift register, okay, that fault stays within that data block. But after the mixed column operation, that fault spreads over the entire column. So when the fault propagates to the entire column, that means it is affecting the data output of all these columns. Then in the round 10, you have this S box 10. Okay, so this fault modifies, and after the shift register operation in the round 10, okay, the fault pattern changes like this. Okay, so you can repeat this entire fault pattern over multiple input values, and you can profile. Okay, you can apply different types of machine learning algorithms depending upon the cipher that you use, and you can devise a set of equations. Okay, and depending upon the algorithm, you may need 2 or 3 faulty encryptions. Okay, that would lower down the key complexity. So AES block cipher has got a 128-bit key size. Okay, that means you need to have that implies 2s to the power of 128 key space complexity, and when you inject a fault, the complexity reduces to 2s to the power of 16. That means for 16 bits, the attacker needs to mount a brute force attack, whereas for the rest of the other bits, he can precisely compute what are the corresponding key values. So this is a very strong fault attack. Okay, that is a differential fault analysis. So coming to a generic block cipher, any typical block cipher, it can be any NIST lightweight cipher. Okay, so presently NIST has proposed Aspen as the standard block cipher, and there are wide variant. Okay, so there are Mongian constructions such as the elephant. So typically, when we talk of fault analysis on any lightweight block cipher, okay, so this is a generic architecture. So what happens over here is that any cipher, okay, it has an iterative architecture. One iteration is called one round, and within a round you have certain set of operations. So the operations are OP1, OP2, and OP3. So suppose 3 operations are there, and you inject a fault on one such operation. Okay, and one operation would involve the key. Okay, a function of the key would be taken in, and this round may be repeated again and again. So the plaintext, that is the message. Plaintext is the original message, and the ciphertext is the encrypted message. So now, when we roll out, or when we perform a time frame expansion or unrolled implementation, okay, so this round can spreads out to n rounds. For instance, in case of AES 128, we had 10 rounds. Okay, in case of elephant cipher, we have 80 iterations. Okay, so depending upon the round location, say suppose on the penultimate round we inject a fault, and then we try to see that how this fault propagates across the subsequent operations. So what we see over here is that the upper branch is basically the fault-free branch, in which no fault was injected. So you have the correct ciphertext or the fault-free ciphertext. Whereas if a fault is injected, okay, that means you have a faulty output from the operation 2 onwards in the round n-1. So you can create a differential between the corresponding operations, that is the OP2 in the fault-free and OP2 in the faulty branch. And then you can track that how the differential changes over the subsequent operations. Okay, and then you can get information about the secret key, okay, in each of these rounds. So this is a typical mechanism of fault analysis attack, okay, on typically any block cipher. Okay, for lightweight ciphers, you have an increasing number of rounds because the operations over there, they are extremely lightweight. Now, coming to the countermeasure aspect. Okay, so when we come to the countermeasure aspect, first is a detection-based countermeasure. In detection-based countermeasure, what happens is that you try to detect, okay, that whether a fault has been injected in an encryption module or not. So now what happens is that when a fault has injected in an encryption module, okay, there would be a redundant encryption module as well. So when a fault has injected, so this encryption module will create a faulty ciphertext, whereas this module will create the fault-free ciphertext, and these two ciphertexts will not be equal. And when both these ciphertexts are not equal, okay, you create a random valve. Or you reset the output. But if there is no fault, then both the ciphertexts will be the same, and you display the correct ciphertext. Okay, but it has got a vulnerability that if a fault is injected in both the modules, then it would lead to the faulty ciphertext as the output. Okay, so this detection-based countermeasure has this vulnerability. As a result, you go to the infection-based countermeasure. So in this case, what happens is that you try to detect that. So in this case, you try to detect a fault. Okay, so and if a fault is injected, you detect it at that operation, and you try to create an infection operation. Okay, you try to infect the subsequent operations. So in this case, the faults are amplified such that the ciphertext, they carry no information about the key. Okay, in this type of countermeasures, also fault attacks are hard, but you need enormously large number of queries, which the lightweight ciphers, they don't allow. So infection-based countermeasures, they form a strong component. Okay, they form a strong candidate for such lightweight ciphers. And then there are fault attacks such as the statistical fault attacks, in which exploit only the faulty ciphertext. They don't exploit the fault-free ciphertext. You inject a fault, you observe the faulty ciphertext, and you try to observe the pattern that how the fault has propagated through the ciphertext. Okay, so it usually needs several faulty several faulty encryptions because you perform a statistical analysis. In this case, you analyze the statistical distribution of the state bytes, and you try to analyze that how the fault have propagated. Okay, so this is a basic idea. So in this case, AES, we again take the case of AES. In AES, okay, you have 10 rounds. So from round 9 onwards, okay, we see that the data, it has got a uniform distribution. Okay, in round 1 and round 10. So you can't create any distinguisher, okay, as the data is uniformly distributed. Now, if a fault is injected in one of the operations, say sub-byte, then it creates a distinguisher because the probability distribution of the data values, okay, they change. Okay, some of the registered bit, okay, they toggle frequently. Some of the registered bit, they can be stuck at, and as a result, the probability distribution of the data value changes. So when the probability distribution changes, you can then easily create a distinguisher to check, okay, that what leads to this change in the probability distribution. So in this case, the attacker does not need to know the cost bias, okay, and we can observe that there are only 4 ciphertext bytes that get infected in the ciphertext, and we can perform this analysis over multiple plaintext and the multiple set of this ciphertext. Okay, and we have observed that the 4 state bytes in round 9 can be calculated, okay, from 4 ciphertext bytes and 4 key bytes, and the complexity of the attack that depends upon the bias that is caused by the fault. If the bias is a large bias, okay, due to a small fault, then you would need lesser number of queries over here. Similarly, there are statistical fault analysis attacks based on the stuck at 0 fault. Stuck at 0 fault with probability 0.5, that means with a probability half, a stuck at fault can be injected, or a logical AND with a random uniform value with a probability 0.5. Okay, so these are the different fault models, okay, that have been analyzed, okay, for statistical fault analysis on AES block cipher. So such analysis can be done on the lightweight ciphers as well. Okay, so certain results are as follows. So fault induced in 1 byte before the last mixed column operation. Okay, so 6 faults in the fault model 1, 14 faulty ciphertexts in the fault model 2, and 80 faulty ciphertexts in the fault model 3. Okay, so what you do is that you partially decrypt every ciphertext back to the faulty cipher faulty byte, and you measure the squared Euclidean imbalance, that is the ACI of this byte, and then the key candidate which gives the highest ACI value is determined as the correct key value. So this is a typical statistical fault analysis on the AES block cipher. Okay, so this is a collision fault analysis demonstration on the AES block cipher, okay, in which you detect between the random plain text. Okay, so when a random plain text, you're giving a random plain text and a fault at the S box, and this is the case of no fault. So the faulty ciphertext and the faulty ciphertext, okay, and when both of these ciphertexts are the same, that means fault does not propagate, then you can easily form a system of equations. And then you can have the statistical ineffective fault attack in which you inject faults, okay, at the S boxes, but those faults don't propagate to the ciphertext output. Okay, so they exploit only the correct ciphertext output, and they require precise faults with the known effect. Okay, so you need to characterize, okay, the entire algorithm to mount the statistical ineffective fault attack. Then you have the statistical fault analysis. Any fault, even if the effect is unknown, okay, it can be mitigated by detection or infection. And then you have the statistical ineffective fault attack that exploits only the correct ciphertext. Okay, so this is a very important attack on the NIST lightweight ciphers. Okay, and strong countermeasures to thwart this type of attacks, they have not been proposed yet. Okay, so this is the statistical fault. So this is a statistical ineffective fault attack. So redundant computation was supposed to fix the problem, but SIFA attacks, they overcome this type of redundant countermeasures as well. Okay, so for simplicity, if we assume the stuck at 0 fault, we could see that the correct ciphertext, they also show a bias up to round 9. Okay, so if we analyze this set of ciphertext, faulty ciphertext, okay, so we can easily backtrack and identify what was the key information for the round 9. So the exploitation work, okay, exploitation module is the same. So this is a typical demonstration of an ineffective fault attack. So over here, so this is an AND gate. The two inputs are A and B, and the output is C. Okay, so if a fault is injected at B, okay, if we get an alarm, okay, that means if we get 0, that means we are sure that one of the inputs is 0. Okay, but if the alarm gets propagated, that is the fault gets propagated, okay, then we are sure that the other input is 1. So whether the fault gets propagated or not, that gives information that what was the value of the other branch. So from this branch onwards, we can easily backtrack and we can create a system of equations. Okay, so we know that A is equal to 1 for sure in this case, whereas in this case, A equal to 0 with a very high probability, that is greater than 0.5. Similarly, for the stuck at fault scenarios, we can monitor that whether an alarm propagates to the output, and whether an alarm propagates to the output. Based on that, we can backtrack, okay, through the circuit architecture. This is the case of a bit flip fault in which we can backtrack, okay, in case of an alarm is raised. So what you see is the output, okay, so the output changes from 0 to 1, and this raises an alarm. And depending upon whether an alarm is raised, we can backtrack. Okay, so the probability distribution, it changes depending upon whether the alarm or the propagation fault information propagates. Okay, that leaks information about the other input values. Okay, so masking is a typical secret countermeasure that has been implemented for against power analysis attack, but we observe that typical fault injection attacks, they are effective on this masking schemes as well. Okay, so on threshold TI based masking scheme also, okay, the fault analysis has been explored. Okay, so these are certain results on statistical fault analysis attacks. On 25,000 faulty encryptions, we can determine the correct key. Okay, whereas in case of a countermeasure, okay, the incorrect key, okay, gives us no information over 25,000 faulty encryptions. Again, for the SIFA, that is the statistical ineffective fault analysis, we can get correct information within 2000 faulty encryption. So this is a stronger attack because you need lesser number of queries, 2000 encryptions only. For the incorrect key, you see absolutely no difference in the probability distribution. Okay, so the statistical ineffective fault attack can break both the fault as well as Parsons countermeasures. Okay, it requires only one fault per computations. Okay, and it has been a major challenge to propose protection countermeasures against such statistical fault ineffective attacks. Coming to the application of the SBox, okay, so there has been a wide amount of research on the SBox constructions. Okay, how can we mask the fault propagations, or how can we increase the fault propagations when a fault is injected at the input of an SBox or within the SBox? So it has been a big challenge to propose such countermeasures. Okay, so I stop over here.
Thank you, Dr. Mazumdar. I think your presentation has very, I think I should appreciate you for doing a fantastic presentation, but showing the starting from the basics, and also you showed the different types of, the fault injection process, so thank you so much for your time today. And, we're ready to take questions, but maybe I'll start with this, questions. I think there's a lot of interest. I think people are working on, modeling sidechain attacks, you name it, whether it's actually looking at from electric vehicle charging stations or, different types of other networks or devices, and what is your take on actually, in especially you talked about transient faults, the effect on the electronic devices, what we have these days, and as the number of embedded electronics is growing in an IoT environment, how do you see physical and clonable functions and quantum play a role in addressing some of the sidechain attacks as a countermeasure? What is your take on that?
Puff actually, the role of Puff is in generating the key. Okay, but Puff has got this reliable Puff has got a big question mark on the aging effect. So if you use the same Puff over a period of years, okay, it has got reliability questions on the key generating mechanisms as well. And when you inject faults in such Puff architectures, okay, that may also leak information. So in that in Puff architectures, the challenge response mechanism, okay, that may leak information. Okay, from the responses, okay, one can get information about the corresponding challenges as well. Okay, in the event of certain faults, because the literature is basically is rich with different types of faults or fault analysis attack. So if one fault analysis attack means if the puffs are resilient, there exists another type of faults, okay, for which the puff may be vulnerable. Yeah, puffs are definitely good in generating the key values, in generating the randomized features, but in the event of fault injections, okay, this randomization parameters, they may go haywire.
Great. And we have a question, but I think, what about your take on quantum in general for hardware securities?
Quantum, I can't comment as of now because the post-quantum cryptographic algorithms, they are coming up. Still, I think they may be hard to break. It would be very hard to come. There are certain literatures that are coming up on the fault analysis aspects on Kyber PQC.
Great. I think we have another question here. And how hardware security can be achieved in devices like pacemakers and defibrillators, considering scenarios where the adversary can control the functioning of the pacemakers by injecting faulty data, how feasible it is to implement security modules like TPM in such critical microelectronic devices that are implanted in human body.
Yeah, so I believe that in such devices, we need to have a proper shielding of the devices. A proper shielding would basically it would screen off, okay, any types of radiations that are being injected. If you try to mount EM-based fault injections, wherein you try to inject the eddy currents within the device, okay, that shielding will basically protect, okay, generating such eddy currents. So instead of putting the load on the hardware, because you have a very it's basically a resource constrained devices. They are resource constrained devices. So in the manufacturing operation only, okay, you need to protect through certain shielding mechanisms. That is my belief.
Yeah, I think your initial slide also talked about, adding security piece may also reduce the life of those devices, right? Or the chip that you talked about. So,
Because they are battery powered devices. So security cores are basically computation intensive, and they would draw even more power. So that may reduce the
choosing
lifetime.
where these countermeasure resides is also another, I think I have a follow-up question on that, and where do you think these countermeasures, even for detection countermeasures, or may reside in when we, what is that? Is it going to reside within the chip at some point?
Yeah. It will reside within the chip, but the major challenge is that in such detection-based countermeasure, you have a redundant component. Okay, means in case of a lightweight ciphers, okay, already you are resource constrained. You don't have those LUTs. Okay, means you can't have that much amount of hardware footprint. Okay, means putting one encryption block, that is already an overhead. And over in detection countermeasure, you are putting two encryption blocks. So that increases the overhead by say almost 10x times. So detection-based countermeasures, there are absolutely no in case of such lightweight ciphers. So we are basically thinking of such infection-based countermeasures in which the overhead would be quite minimal.
Yeah,
we try to detect which operations are more vulnerable and protect only those operations.
No, that's right. Even running this, you need to know when we should run even this detection thing,
right,
because that's going to draw power, right? I think. Anyway, I think we have another question. Thank you for your presentation, Doctor. From asking on lightweight ciphers, can you share your comments on the feasibility of leveraging parallelism in modern processors to balance overhead and security? For masking on lightweight ciphers, the masking does not work, according to literatures. That's the question is the feasibility of leveraging parallelism in modern processes to balance overhead and security. Are we assuming that you have the computational capability to run on, I'm not sure, how do you to balance overhead and security? Overhead is already there, right? Like you talked about.
Yeah, overhead is
already there. So I think could you balance it? Of course, that's a trade-off that people are actually looking at. And I don't know. I'll let you answer that question if you think you have any comments, or maybe.
So in such cases, means you need to have a mechanism in which you need to stop the fault from propagating to the output. In that case, means that would create enough randomization at get the output. Means you need to have a certain mechanism. Okay, right where the fault is injected, means whether you can stop the fault propagation from that point onwards. If that can be done, I think masking is well and good.
Great. One other thing, we are doing in a couple of other FAA funded projects on electromagnetic, based, we're trying to understand this, how to do this. But you mentioned about electromagnetic probes, right? And could you talk about injecting side channel attacks using EM? How do you think from your reading or from your work, what you have understood, how do they carry this EM thing? And nowadays software-defined radios, everything is coming, at a low cost. You mentioned EM probes, right? Could you shed some light on how that is done?
So basically, the EM probes, they can be in the form of differential probes, and they act like an antenna. Okay, so basically they create a variation in the electromagnetic field, and the result of the variation in the electromagnetic field, okay, the current that is being drawn from the battery, that current value, it changes. Okay, and as a result of that current change in the current value, okay, certain data bit registers, okay, they may get flipped, because when you are changing the current value, it may flip the certain data values in the registers. So depending upon the path, okay, means that kind of an attacks are basically a tailor-made attacks, wherein you need to have the precise information about the entire architecture, how is it implemented. Okay, in certain cases you may need to flip open the chip and identify, pinpoint, okay, which are the registers. You may need to reverse engineer first and then try to see. So that is basically a stronger attack, but there have been attacks that have been mounted on just bare ICs.
Right. Let's see. So we have a lot of students listening, and this webinar is also recorded, and what are the research challenges, for the next students who are listening to this for dissertation, or you mentioned SIFA as a challenge, right? And
right.
what is the main research gaps if somebody wants to pursue this area as their topic, and what are those couple of open-ended research problems that they can look at?
So basically the major research area is to propose optimized countermeasures for such lightweight ciphers, because the challenge is on the platforms itself. The platforms don't give you enough computational resources. Okay, this how can you minimize, okay, the countermeasure part, because security means encryption is always an overhead. And now in the literature you have this authenticated encryption schemes, wherein the same cryptographic primitive will give you the encryption feature as well as the authentication feature. Okay, and over there what we are observing is that the authentication part, the authentication branch, is more vulnerable towards fault analysis attacks. Okay, so now the question is whether you would go for protecting this authentication branch or whether you would go for protecting the encryption branch. Okay, which one would you choose? Which one would be easier to protect? Obviously, we have observed from the literature that the authentication is much easier to mount an attack, because over there means the nonces don't come into the play. The nonce are the random values. So whenever you have the random inputs, that actually makes the life of the attacker even more harder. So the attacker usually targets the authentication part. So pinpointing, so given an architecture, okay, what is the fault exploitation space? So if you have, say, suppose a Cipher suite, means say suppose a suite of encryption algorithms, okay, and if all those algorithms are implemented on a certain platform, be it a software platform or be it a hardware platform, okay, how do you characterize the fault exploitation space? Which are the hotspots, okay, within that implementation that leaks information? Okay, because it would be a foolish act to protect the entire architecture. So first you need to characterize that, okay, that which are the hotspots, okay, that leaks maximum information. So you would obviously protect those hotspots only, so that the fault does not propagate to the output from those hotspots. Or if there are countermeasures, say infection-based countermeasures, how do you use those countermeasures to protect such hotspots?
Cool.
And obviously the PQC is obviously a big challenge. Means how do you implement countermeasures for fault attacks on the PQC hardware?
Very nice, very nice. Last question, I think, in the interest of the time, I think you mentioned somewhere that for data retention, cooling. I saw some what do you see about cooling phenomena for data retention? Could you shed some light there? I think
I don't have much knowledge in that perspective.
Okay, so are you trying to say that by using cooling phenomena, we can able to retain some of the data during those
right.
adapted phase? Maybe that's what.
Maybe.
Great. I think we don't have any more questions, and I think it has been a very enlightening. I'm sure others will also appreciate your time. And what we'll do from now is if you can email your mailing address, we will send you a nice plaque from our Center for Cybersecurity, and also a nice certificate from our dean, and thanking your contribution. And I think we need to continue to engage with you to learn more, and maybe find ways to collaborate with you to see, and how. Great. Thank you so much for it, Dr. Mazumdar. I'll be in touch with you by email. I appreciate your time today.
Thank you.
Thank you.